Let's talk about exploring data visually. In order to examine the distribution of a set of data, we often organize and present data using tables, charts, and graphs. The type of data will help us determine an appropriate visual representation. So for categorical data, which breaks up measurements into categories, the most appropriate graph types are bar graphs, pie charts, and frequency tables. And here you'll see examples of each of those. So the first graph here is a bar graph of the frequency of color of Skittles. And this might be in a pack, but you'll see that there's mostly red, followed by green, then purple, and then yellow and orange are about the same. And on the y-axis here, we have the frequency, and on the x-axis here, we have the color. So this is categorical data. You have categories, and you're representing the frequency by the height of a bar. Here you see an example of a pie chart, also known as a circle graph. This is best for representing the part to the whole. Okay, so you could have done the same thing with the Skittles. You could have shown what percentage red was out of the whole pack of Skittles. So here we have favorite ice cream flavors. That's categorical because the responses are in categories. And then we've got the relative frequency, also known as percentage. And these percentages have to add up to 100%. Otherwise, we've got an incomplete and incorrect circle graph, pie chart. Okay, so here we can see chocolate, 40% of respondents in this sample prefer chocolate. Vanilla is the second most popular, 35%, followed by strawberry, and then my favorite mint chocolate chip. I guess I'm in the minority of this sample here, which may or may not be representative. And then down here you've got, sadly maybe, the most commonly used chart for categorical data that I've seen anyway in research is this kind of boring looking frequency table. But it's very, very commonly seen in written research, published research. So you've got the categories here. You've got 4 different categories, and then they have a total row as well. And then they display the frequency. So this is the actual number, the count in each category of responses. They converted those to percent. Then you see this thing called valid percent, which these are actually the same, which means that everyone responded. If you had certain people not respond, the valid percent would be different than the percent, and the valid percent would be the percent of those who responded, where the percent would be the percent out of the total sample members of the sample, whether or not they responded. So I tend to look at the valid percent to get a better idea because that includes those who responded. And then you have the cumulative percent here, which kind of adds as you go. So notice it starts with 38%, and then 52% were Republican, so you add that to the 38, and you get 90%. So that means 90% were Democrat or Republican. And then you add the 8% that were split, and that makes 98%. So 98% were Democrat, Republican, or split. And then the remaining 2% give you this 100% nonpartisan. Cumulative percent always adds up to 100. And you could use these valid percents or this percent row here, column, to make a pie chart as well. And the cumulative adds as you go. All right, for quantitative data, you get histograms, box plots, and stem plots. Those are the most commonly used plots for quantitative data. And this is called a histogram. It looks a lot like a bar chart, like what we saw with the Skittle flavors, but there's no gaps between the bars because this is actually on a continuous scale. Okay, so it's not categories down here on the x-axis, it's BMI. So they all flow together. You go from 18 to 19 to 20, but someone could have a BMI of 18.5, let's say. So that's why there's no gaps visible here. The bars touch each other. And then on the y-axis, you have the frequency, the number of individuals with each body mass index. Here's the sample size. We've got a title. This is actually a well laid out graph here. This is a good histogram. Well done, whoever made this histogram. You've got the title. The axes are labeled. The y-axis starts at 0, which I like. We're going to see examples later. What happens when you don't start the axis at 0? It's not always appropriate to start at 0, but usually if you can, you should start an axis at 0. Notice they don't start the x-axis at 0. That's okay. That's because it's very rare to have a BMI less than 18, and no one in this sample seems to have that. So anyway, this is an example of a histogram, and we can use it to kind of see the shape. I mean, if I blur the lines here and I look at the shape, I can see a mound-shaped, like almost a bell-shaped curve going on here to model this data. It peaks right in the middle, around 25 or so. So the average body mass index, you might guess, would be around 24 or 25, and it ranges between 18 and 31. So that gives you an idea of how spread out this data is. This second example here is called a box plot. What it does is it breaks up the data into percentiles, 25%, or quartiles, you could call them. So this is a quarter of the data, this little whisker here. This first half of the box is a quarter of the data. And then this other side of the box, this line in the middle is the median. So that's one measure of center. This is another 25%, and then this whisker up here is the final 25%. So it gives you an idea of the quartiles and how spread out each quartile is and whether or not you've got skewed data. This is roughly symmetric. I mean, the whiskers are about the same size. The median is roughly towards the center of the gray box, which represents the middle 50% if you put these two quartiles together. So it's roughly symmetric, but you've got these little floating asterisks here, these floating dots. Those represent outliers. Outliers are far outside the pattern of the rest of the data. So you've got several high outliers here. So this is the age of Best Actress award winners. And so you've got some that are older than what is typical. Okay, so the average, the median actress is in their early 30s when they win the Best Actress award, but it looks like you've got one as old as 80. Okay, so that's a box plot or a box and whisker plot. This is called a stem plot or a stem and leaf plot. This is final sale price to the nearest dollar of some item. Here's the key, 8 bar 0 means 80. So the way this works is if you see this 8 and then this 9, that means 89. So there were two final sale prices of 89, $89.89. You can also kind of see a shape here. You see the mode. You see most final sale prices were $65 because there's so many 5s next to this stem of a 6. And the benefit of using this, I can also see a suspected outlier. This may be an outlier here because there's nothing in the 110s, 120s, 130s, 140s, but all of a sudden $150 is a final sale price of some item. So there's a big gap here, which leads me to believe that this is an outlier. But the great thing about a a stem plot, that's not true of a box plot, or really a histogram, is this preserves the original data values. So you can see every single number that was in the original sample. So 34, 34, 35, 52, 61, 61. You can use this stem plot to reconstruct the original data. It preserves the original values. Here's just a little tip about making and reading graphs and charts. A visual representation should be clear, easy to read, and self-explanatory. So these I just stole from research articles with no other context, and they're pretty clear on their own. They're missing some details. We don't know what they're talking about here, but I can tell that these are the final sale prices of some item. Watch out for axis labels, scale, 3D, the area property, etc. So I'm going to talk about good graphs and bad graphs and what these tips lead to. So here's some examples of what I would call good graphs. They're clear, they're self-explanatory. They have a title, weight distribution at 18 years of age. The axes are labeled, percentage. They both start at 0 here, which is a good thing. Weight distribution at 18 years of age and percentage. Okay, so about maybe 4% of these individuals weighed between 40 and 50. Is this pounds? Let's see. So that's hard to tell. It should tell me what the units are here, but I'm going to guess it's pounds. 40 to 50 pounds, about 4% in Pelotas, Brazil. All right, most of these individuals were between, I would say, 60 and 70 pounds at 18 years old. All right, that seems very light now that I think about it. This may not be pounds, I'm not sure. We'd have to go back to the original study. So there's a flaw, is we don't have the units on this. And it's a pretty large sample size, 2,194. And I can see the shape is roughly unimodal. There's one peak. It's got a little bit of right skew because there's more data spread out after the peak, okay, to the right of the peak. It's got a longer tail, we would say, but it's roughly mound shape, a little bit askew to the right. No suspected outliers on either end. I don't see a random bar here or here. I shouldn't say random, but a bar after or before a gap. Okay, and the center is around 65 or 70. These are also pretty good graphs, although I see some flaws, so I'll point those out. I love finding flaws. These are from the same study. Here's a frequency table. So you've got absolute frequency, which is the sample size. So 1855, 1855 said no, 559 said yes to whether or not they had acne scars in 18-year-old adolescents. Okay, so more had acne scars than, or more did not have acne scars than did. And here's the relative frequency, which is percent. This helps you put it into context. 77% roughly did not have acne scars, and about 23% did have acne scars, which adds up to 100%. And then this is the same data here, just displayed, I believe, as a bar graph. So you've got yes versus no. This is categorical data, so we have a bar chart. The only flaw that I would point out here, I mean, they have a little description, which is nice. The scale is the frequency. A flaw that kind of bothers me is does this yes bar look a little bit narrower to you than the no bar? These should be the same widths. Okay, they should be equally wide. Otherwise, it kind of shrinks to your eyes, the area of this bar here. So that's something I would point out as a pet peeve or just something that I think could be improved. Okay, and then finally, they take this same data and then they put it into a circle graph. They use these relative frequencies that we saw before in a circle graph or a pie chart to show you the difference here, okay, to show you the relationship of the part to the whole. So overwhelmingly, 18-year-olds did not have acne scars in Pelotas, Brazil, based on this sample, which we could look into how the sample was collected to see if that has anything to do with the results that we're looking at. All right, so these are decent graphs. Here's a bad graph. Here's something that's correct but misleading. I stole this out of a real research article. So you've got treatment versus placebo. Those are categories. And then you've got a bar for preoperative score and a bar for postoperative score. The first negative here is we don't have a title. And we don't have an axis label here. Okay, so we don't know what these numbers represent. Okay, but I'm going to say maybe they represent self-reported comfort level or something. Let's say that this is a score on how well the patient is doing on some measure. So preoperative is low, postoperative they're doing better. Okay, so I think we're using these bars to see improvement in some score, right? So wow. This is treatment versus placebo. Now, if you don't know what a placebo is a fake or inactive treatment. Okay, so what we're seeing here is a slight improvement before operation and after operation with the placebo, and that's something called the placebo effect. This is not surprising that when you think you're given a treatment, just thinking that you're taking an active treatment improves your health in some ways. Okay, that's a known phenomenon, psychological, psychosomatic phenomenon. So we see a little improvement here, but we see a much bigger improvement with the treatment. So some treatment was given and we see a big jump in score. Now here's what's wrong, here's what's misleading, is this scale, I don't know if you noticed, it doesn't start at 0. So I'm gonna do the big reveal here. If I start the scale at 0, this is the same data. I'm not manipulating the data. It's the same data, I'm just changing the scale of the y-axis here. And do you see what happens here? I mean, this first one, by starting at 1.08, and going to 1.24, you're kind of zooming in on that section here, and it almost looks like the postoperative improvement here was like triple this blue bar here. It's triple the size. But really, what was the change? We went from 1.13 to 1.23. So there was a change of about 0.1. Okay, and here's what a change of 0.1 looks like on a scale that starts at 0. So the difference is not actually as big as it really looked in that first graph. Okay, so it's correct because the numbers are plotted correctly in both cases, but by changing the scale, you're exaggerating differences, so it can be misleading. Here's another one from 2010. This is from President Obama's actual State of the Union address. They showed this visual where the GDP, which is a measure of wealth of a country, of the US was around 15 trillion. China, the second biggest, was around 6 trillion. So the US is almost 3 times the size of the GDP of China. And now here's what they did was they took the diameter of this China circle here, the diameter, which is the distance across, and it's roughly tripled, 1, 2, 3. You could fit about 3 diameters. So to show an increase of 3 times as large, they tripled the diameter. Now what's misleading about that is that when your eyes look at a circle, you don't look at the diameter. What you look at is the area, which is the space that it takes up. Okay, and if you think about this, if I had a 1 by 1 square, right, that's 1 square foot. Okay, 1 foot by 1 foot, that would be 1 square foot. 1 times 1 is 1. And then if I double the side length of the square, so now I have a 2 by 2 square, 2 feet by 2 feet. The area is 2 times 2, 4. So if you double the side length, it quadruples the area that you're looking at. Same thing with a circle. It doesn't matter which shape. If you triple the diameter, you're actually doing 3 squared, which is 9. This circle is actually 8 or 9 times the size of this circle, okay, which exaggerates the difference. So let me show you what it should look like. Okay, so in pixels, 40 to 64 is the same ratio as 5.7 to 14.6. So this is what the difference should look like. This circle here is 2.5 times or 3 times, almost 3 times as large as the China circle. Okay, so this is better. I'm going to go back to the slide just to remind you. That's what was presented using diameters. Here's what it should look like using areas, and that's a little bit more accurate based on the way that humans look at two-dimensional shapes as we look at the amount of space it takes up. Okay, when you're looking at a histogram, you should pay attention to 4 things: shape, outliers, center spread, SOCs. The shape is the overall pattern, which I'll show you some typical patterns. Outliers fall outside the overall pattern, so look for gaps. The center is the balancing point. Okay, it's not always the peak, but if the histogram or if the box plot were a solid piece of material, where would it balance? And then the spread is the range or the variability, how much the data varies, how much it's spread out. So here's some common shapes. This is one of the most commonly seen shapes here. It's a typical mound-shaped symmetrical histogram. Symmetrical just means it's like a mirror image on the left and the right. It peaks somewhere towards the middle. Okay, we might also call this bell-shaped. This is a typical uniform or rectangular histogram where every bar is about the same height. They don't have to be perfect like this, but if they're about roughly the same height, we call that uniform. These are very important to understand which is which, and it's easy to confuse them. So this is called a left skewed histogram. It's skewed to the left because it's got a longer tail to the left. It takes longer to kind of ramp up. It's got a longer slope to the left, and then it peaks later here, and then it drops off quickly. That's skewed to the left. This is the mirror image of that, skewed to the right, where it peaks early, and then it has a longer tail to the right. Okay, so skewed left and skewed right depend on where their longer tail, the longer gradual slope is, not where the peak is. All right, so keep that in mind. Skewed left doesn't mean it peaks to the left. It means it peaks to the right. And we give it those names because of what it does to the mean. When you're skewed to the left, it'll pull the mean towards the left, and when you're skewed to the right, it'll pull the mean towards the right. We'll talk more about mean later. And this is bimodal because it's got 2 humps, okay, 2 mounds or clusters of data. You could also be trimodal, multimodal, but if you've got roughly 2 clusters here, you're called bimodal. And here's an example of a box plot. The box plot is based on the 5-number summary, and it breaks up data into quartiles, 25% in this whisker, 25% here, 25% here, and 25% here. So 4 quartiles, and the median is right in the middle of the box. The box represents the middle 50%, okay, the middle half of data, which would be typical, is between Q1, which is the lower quartile, quartile 1, and quartile 3, the upper quartile, the 75th percentile. Okay, and the median is the 50th percentile. So 50% of data is below the median, 50% of data is above the median. And I would describe this as roughly symmetric. The whiskers are about the same length. This part of the box is roughly the same size as this part of the box. It's a little bigger here, but the median is close to the center of the boxes. So this is roughly symmetric. It's not really skewed strongly in any direction. Okay, and we've got temperature here. So let's do an exercise. Let's actually explore something. So this links to the notes that you guys are able to download and look at and read and go back to. So we should have an exercise down here past where we were just looking. Here it is. So I'd like you to try this with me. You can pause the video and you can go through this several times. I've got data here. A survey of enrollment at 35 community colleges across the United States gave the following figures. Determine the data type. All right, so I'm going to copy this into a Google Doc, which if you'd like, you could use Microsoft Word, whatever word processing software you use. So I just opened a blank file. I am going to copy and paste. Okay, so determine the data type. So let me put my answers down here. Okay, what type of data is it? All right, so it's numeric. We can see that they're numbers, right? They're counts. They're numbers of enrollment, right? So 6,414 students enrolled at one community college. This is quantitative data because it's numeric and it makes sense to kind of figure out what's the average enrollment, where is the enrollment the largest. If you can do algebra, like if you can find the total enrollment or the average, if you can do operations like that, it's quantitative. Quantitative, which also means it's numerical. Okay, I'm also going to say that it's discrete rather than continuous because it's countable, and also because it's whole numbers. Okay, so you would count the number of students. It's not like you would have 9,350.5. You wouldn't have decimals. It's whole numbers. So that makes it discrete data. Okay, so that's going to lead us to part B. Analyze the data graphically by creating one or more graphs and provide a description of the figure. All right, so based on the data type, for quantitative, gotta make sure I spell correctly, our choices would be histogram, box plot, or stem plot. And I might do all three because if you're happy and you know it, you do all three. Let me zoom in a little bit here so you guys can see a little bit better. I hope that's better. Okay, I'll move the editing bar. Great, so let's do it. So I'm gonna hit enter a couple of times. So I'm gonna show you how to do this using technology. All right, and there's several different options for technology. If you're good with spreadsheets like Microsoft Excel or Google Sheets, feel free to analyze it that way. But I'm gonna highlight this data, all right, and I'm gonna copy it, Control C or Edit Copy. And I'm gonna open a new tab and I'm gonna go to a website called Staplet, which there's gonna be a link to that in the description of this module. So staplet.com, or you could just Google Staplets. It stands for Statistical Applet. An applet is like a mini app, okay? And we're going to stick to this top part here for now, and we're only going to use a couple of different options. So you've got categorical variables and then quantitative. Like I said, this is a quantitative variable. So we're going to stick to one quantitative variable single group for now, one quantitative variable. The variable is enrollment, right? All right, so you get to this screen here, one quantitative variable, single group. The variable name is enrollment at community colleges. This is how it's going to label the graph. All right, so you put a little title in there. We're going to input the raw data. I like my data raw, like I like my sushi. All right, so I'm going to paste if I can. Let me copy and paste. Did I copy already? I think I did. All right, copy and paste. Okay, it says separated by commas or spaces, but semicolons also work. And once you paste all your data in there, or you type it by hand, if you like typing things by hand, you hit Begin Analysis. All right, and here's what I get. It comes up with a dot plot, which that's perfectly fine. It puts a dot at each value along this axis, but click the drop-down menu, and I like histograms. So we've got a histogram. Yours might be blue, all right, because I think the default is blue, and I have played around with this color here. So let me make it look more like what yours might look like. Okay, blue. or go back to default. That's good. All right, so this is what yours should look like. How do I get out of here? I might have to move this little toolbar. There we go. Done. All right. Great. So yours should look something like this. This is probably what it looks like. So here's a histogram. Enrollment at community colleges. So from 0 to 5,000, you've got 10 community colleges that enroll between 0 and 5,000. You've got 16 community colleges. You can see the height of the bar is the frequency between 5,000 and 10,000. And this is ready to go. Okay, just in a few clicks, just by pasting the numbers and choosing histogram, this is ready to go. So I'm going to actually screenshot this. Okay, and if you don't know how to screenshot or screen capture on your computer, just Google how to do it on your computer. Okay, so I'm going to screenshot. I'm going to go to my little document here. Okay, and I'm going to put a histogram. So I'm going to insert this. Let's see, I need my editing thing, I think. Insert image. Upload from computer, and it should be somewhere on my desktop. Screenshot. There it is. Let's shrinky dink a little bit. All right, and this is perfectly acceptable when you guys do a test or a quiz or a homework, or if you're doing real research. This actually looks really nice. Okay, so this is that. I might want to put a title on it. It doesn't have a title, but right above I might write histogram of enrollment at community colleges. All right, and let's describe the shape, right? The shape, this peaks early and then has a longer tail to the right. So this is called right skewed. I'm going to start describing this. Okay, the shape is right skewed. The enrollments appear skewed right with, do you see any outliers? I mean, there's no gap in the data. In other words, there's no gap where there's no bar and then all of a sudden there's a bar way up here or something like that. That would indicate an outlier. So I'm going to say no apparent outliers. SOX, shape, outliers, center spread. So I'm going to end the sentence there. The typical, or the most common, no, I'll say the typical community college enrolls around. All right, so if this was a solid material, where would you try to balance it? You'd try to balance it somewhere near this peak here, maybe around 10,000. That might be a good spot to estimate the center of this distribution. Okay, it's going to be close to the peak, but because you've got a longer tail here, the balance point might be around here. And we're going to learn more precise ways to figure out the measures of center. But for right now, I'm going to say around 10,000 students. Okay, the typical community college, I'm going to say in the sample, because this is not a complete sample. It's only 35 community colleges. And I'll say with a range of at most. So the range goes from the minimum is 0, the maximum is 30,000. In just looking at the visual, we can actually look at the original data to find the minimum. There was no community college with 0 students. Okay, so that's why I'm saying at most. The lowest possible is 0. The highest possible is 30,000. So at most 30,000 students. Okay, so that's a pretty big spread. There's a spread of 30,000 students at most between the smallest and the biggest number based on this graph. Okay, so that's shape, outlier, center spread, SOX. Let's look at a box plot. Where's my box plot? Let's see, here it is, Staplet. So, oh, by the way, you can play around also with, so Staplet picks a default kind of range, 0 to 5,000, but let's say you wanted to go from 0 to 2,500. You could enter your own range there and you get twice as many bars, okay, and you can start to see little gaps here. It still peaks early. I would still call this right skewed, but you have more bars here, okay? And if you do less bars, let's say we wanted to count by 7,500, right? Still kind of the same shape, just you have one fewer bar. So I'm going to stick with 5,000. I think that was kind of nice. All right, so that looks pretty good. But if you wanted to adjust, if you want to count by 1,000, count by 5,000, enter the interval width. That's what you're counting by. Okay, and boundary value is where you start. All right, so it's starting at 0, which again is good practice. Okay, box plot. Here's a box plot. There are outliers. We didn't see them in the histogram. That's one of the disadvantages. The box plot clearly shows that there are 3 colleges here, community colleges, with outliers. Okay, and this is the highest maximum that's not an outlier. All right, so that's an advantage to the box plot. Very nice. And you can still see the right skew here. Look, I mean, the box is pretty symmetric. The median's in the middle. What shows that it's skewed is you got a much longer right whisker. Okay, this tail here is much longer. If the right is longer, there's more spread in the upper 25%. It's right skewed, okay? This is a shorter whisker here than this. And then you do have outliers here, all right? So again, you can screenshot this, okay? Just screenshot this and put it right into your document that you're working on. Okay, so maybe I'll add that to my document. I'll also upload this so you guys can see it. Insert image. Should be the most recent screenshot. There it is. I'll shrink it a little bit. Okay. Oh, I don't need it to say box plot, so I'm going to crop. Whee! There we go. All right, if you don't know how to crop something, you can also Google, how do I crop on my computer? All right, that's good. And if I give a description of this, the box plot of enrollment displays some right skew with 3 high outliers. Okay, that's why notice I didn't say, I never commit to anything. I didn't say anything definite here. I said no apparent or no clear outliers. But they are clear here. Okay, so it turns out, and this is the same data, there are outliers. Maybe that's why this bar was a little bit higher than the one before it. Okay, with 3 high outliers. And then I'll also say shape outliers, center spread. The median enrollment appears to be about, it's here, I would say it's about 65, what is that, 6,500? 6,500 students. Okay. See, shape outlier, center spread. And the middle 50%. If I have a box plot, I would say how spread out the middle 50% is. This is called the IQR, the interquartile range. Interquartile range, or IQR. The middle 50%, let's see, it goes from about 3,000 to about 10,000, so that's about 7,000. The middle 50% spans about 7,000 students. And I'll put in parentheses how I got that. I got that 3,000 to 10,000. So if you subtract those, you get the interquartile range. 7,000 students is the range of the middle 50%. Okay, that's one measure of how spread out things are. So how spread out is the middle. Great, that's good. So those are the 2 I would do. Box plot. You could do a stem plot, but I don't think it's going to look very good with this data. Let's look at a stem plot. Yeah, this is, so 1263 was the minimum. Then there's a big gap. 1550. I mean, this is not a good stem plot. It's got a stem for every 4-digit number, and it's just really spread out and cumbersome and impossible to read. So let's not look at that. Let's go back to histogram. That was kind of my favorite representation. And down here, they have the numerical measures. So they tell us what the mean is. They tell us what the median actually is. They tell you the quartiles, the minimum, the maximum, the standard deviation, the sample size, and you can export those to Excel if you'd like. Okay, so that's how you play around with data. That's how you make visualizations of data. This can all be done by hand, but in this day and age, no one's doing this by hand, and I think Stapplet is a nice, clear way to do it. And this is how you might see charts and graphs in published research. All right, we're going to do part 2 next.